Okay, let me
We're
just...
live.
Yes,
Hello?
we are live.
You live?
Yes.
Yes.
Oh, wow.
So I will do the introduction for you. So again, hello everyone. Welcome to the third installment of the GPMO/ScaleML session in the summer. So today we have excited to have Chris coming to talk about very cool work. So a little bit of introduction about Chris. Chris is associate professor in computer science department at Cornell University. He's a member of Cornell Machine Learning Group and leads the Relax ML Lab. So his research includes algorithmic, software, and hardware techniques for high-performance machine learning systems with a focus on relaxed consistency variance of stochastic algorithms such as asynchronous and low-precision stochastic gradient descent and the MCMC. So the Relax Lab that he built toward using these techniques to construct data analytics and machine learning frameworks, including for deep learning, that are efficient, parallel, and distributed. So today we'll have Chris teach us how to do quantization.
Take it
Great
away.
for having me. I hope you all can read what I've written. At least I seem to be able to read it, so on some level it's visible. Today we're going to be talking about quantization, and in particular, most of what I'm going to talk about today looks at post-training quantization, and at the end I'll get into quantization during training for a bit. But what I want to run through is a line of work from my lab that understands quantization in a bit of a theoretical way, is able to characterize it mathematically, uses this to derive methods and propose techniques that actually get good performance empirically. And then some of these results, it turns out, also are applicable to other quantization settings, such as for training. So this is, as you might guess, a whiteboard talk. So I'll be going fairly slowly through things. If you have questions at any point, please ask, and I'll try to adjust to what you guys are interested in. But to get started, I'll just mention, what is post-training quantization? Why do we care? Basically, the idea is you have some machine learning model, and you want to run the model on some device, and the model is too large. And so either the model has too many weights to fit on your device, or maybe the model can fit on the device, but it would require too many flops or too much energy to compute. So what we do is we convert this model into a smaller model with fewer bits per weight. That's the idea. And quantization post-training is different from quantization during training, in that when you quantize during training, when you do something like quantization-aware training, you have a model that is quantized, that uses a small number of bits per weight in some sense throughout the whole pre-training process, or maybe throughout a significant amount of fine-tuning. Whereas with post-training quantization, we are in a regime where we have a model that starts out in full precision, whatever you consider full precision to be, FP16, even FP8, sometimes people call that full precision now. And we want to make it smaller for some deployment tasks. So what are the desiderata of post-training quantization? What do we want? Well, obviously we want the model to be smaller. I'm not blocking. Make the model smaller. But equally importantly, we want to make inference fast. So that is, when we're doing post-training quantization, when we're choosing a way to represent our model in fewer bits, the goal is not just to produce a compressed version of the model that uses fewer bits and that could be decompressed to produce the original model. Rather, we want to produce a smaller version of the model. Let me just move this over a bit. We want to produce a smaller version of the model that can be used to compute predictions using the model faster than what we had originally. And the third desiderata usually is that we want to do this, without too much work. Not too much time / compute. That's terrible. Compute to compress. And the reason why this is sort of a desiderata is that if we were willing to spend a huge amount of time, a huge amount of work to do the compression, if we're spending a lot of time like doing backward passes, doing fine tuning on our compressed model, it sort of stops being post-training compression and starts being quantization-aware training or compression during training or quantized training. Okay. The setting also that I'm thinking of here is the setting of weight compression. So at the moment, I'm not going to talk about activation compression. Lots of methods do both activation compression and weight compression, but for simplicity to sort of run you through the line of work that I'm going to talk about here, I'm just going to do weight compression. And in particular here, what does weight compression mean? It means that the thing that we're compressing, the thing that we're taking and making into a lower bit format, a compressed format, is just the weights, just the parameters of the model, not the intermediate activations that are being computed during the forward pass of the model. All right. So that's a setup. How do we do it? Well, okay, naively, when we compress, we are just going to reduce the precision of the numbers in the format. So I would have my weights, and I would just take those weights and I would round it to some lower precision format. So for example, if my weights I want to store in, say, int4, then I just do something like weights.to int4, and imagine that this code took each of the weights of my model and rounded it to the nearest int4 representable number, modulo some like scaling and whatnot. Right? That would be what we would do naively. And people have tried this historically. It actually does work pretty well for relatively large number of bits. Like for int8, you can kind of do something like this. But for more, or for lower order bits, or for lower bit counts, this doesn't really work all that well. And the reason why it doesn't work all that well is that, well, when you just round naively, right, you're introducing a bunch of quantization noise, a bunch of rounding error. And that rounding error is going to introduce, eventually, as you reduce the number of bits enough, too much noise for your model to handle. Machine learning models are typically pretty reliable, pretty robust to noise. If you add like a little bit of random noise to the activations, a little bit of random noise to the weights, they will work just fine. But eventually you get down to a small enough number of bits, producing a large enough amount of random noise that the performance of your model is just really damaged. So, okay, this suggests, right, another important desiderata when we're doing post-training quantization is that we not only want to make the model small and fast, but we also want the compressed model to be close to the original. And when we talk about quantization compression here, it's lossy compression. So we're not actually producing the same output. We're producing output that's approximate and that's hopefully close to what the original model would have produced. Okay, so just naively rounding is empirically doesn't work for most applications. So how should we round? How should we compress? Well, let's think about these desiderata here, about what we want to do. And I'll think about the last one first. I want to round. I want to produce a quantized model that is close to the original model. And really what that means is that it's making predictions that are close to the original model on some distribution. So one way that we can think about this is in terms of an objective that says I want to minimize over some parameter vector, which I'll call W. Let's call it W hat in some quantized representation. This is a little bit awkwardly written. I'll just say, Q, where this is not the natural numbers, but in the set of possible quantized weights. The difference in expectation of the output of the original model, which we'll call F, of the quantized model versus the original model on some example drawn from the data set. So if D is my data set, X is an example from the data set, then we want to minimize some difference in terms of what the output of the model is. And depending on what your output is, it could be anything. For text, we often want the KL divergence. Or I guess this is double bar, you can write the KL divergence, where you're basically comparing two output distributions over a discrete space between the quantized model and the original model. Basically saying how far away am I on average on a given data set. If we could solve this optimization problem that I just wrote down tractably, then we would be done. Post-training quantization would be really easy. Spoiler alert, we can't solve this optimization problem exactly. This is like as hard as training or as hard as distillation, and you have quantization involved. It's just difficult, right? But one thing that we can do instead is we can say, well, when I do something like this, when I want to minimize this error, I can approximate it by leveraging the fact that W hat, the quantized model, is probably pretty close to W, right? When you quantize, when you round, you're not trying to produce something that's like really far away. You're trying to produce something that's relatively close to the original model. And so what people do is they approximate this objective with a second order. I don't need these by value. They approximate it with a second order approximation. Yeah, a second order expansion, basically. So what I'm going to say is that this is equal to some quadratic form that looks like W hat minus W transposed times H times W hat minus W, where here I'm treating these W's as weight vectors, and H is the Hessian, or the second derivative matrix of this loss function at W. And the reason why this is approximate and why there's no zeroth order and first order terms is that because we are evaluating a distance to the original model, the zeroth order term is just 0, because when you're at the original model, this is 0. And the first order term is also 0, because trivially, this expression is minimized over the real numbers at W hat equals W. So W in particular is a local minimum, so the derivative is 0. So you get this type of quadratic form. Okay, so super. So far, so good. We can just minimize this quadratic form, right? Well, not so fast. This is also intractable. This is almost worse. This is almost more intractable than the first thing. This is basically saying I'm going to produce some Hessian, some second derivative operator over the whole weight space, which is going to have size equal to the number of weights squared. So that's no good. So what people do instead is they approximate this with some Hessian sketch. So I basically say, I don't know how to compute H, the actual Hessian of the real model. I'm going to approximate it with something. And then I'm just going to quantize in order to minimize this approximation. I'm going to choose the approximation in a way that seems to make sense and in a way that's tractable to compute. And the most common approximation that people use is the one from a paper called adaptive rounding from a few years ago. It was also very prominently used in GPT-Q. And the strategy is to do the quantization, to do the approximation at the level of an individual linear layer. And you approximate the Hessian of the whole model by looking at the reconstruction error on the data set of the activations after that layer. So concretely, if I have a linear layer with weights W, it's getting in some input from earlier in the model. So if you think about this signal X, that's not the original example from the data set. That's just whatever is coming into this linear layer from the original model. And then what we imagine is that if this is Y, where Y is equal to WX, we're imagining that we consider a quantized version of this layer, which also gets in the same X. And now it's going to output Y hat is equal to W hat Y, where again, W hat is the quantized version of the weights, and Y hat is just the result of using that in a linear layer. And then the approximation that it produces is that the loss is the expected value of the norm between WX and W hat X squared. So this is just an expected mean squared error, where this expectation is taken over examples in some data set. And typically, we call this data set a development set or a calibration set. And it's pretty easy to show that you can write this as the trace of W minus W hat times H times W minus W hat transposed for some Hessian matrix H. This is not, to keep clear, this is not the actual Hessian matrix of the real model's loss function. This is the Hessian matrix of this proxy. So this whole setup reduces the construction of post-training quantization to just minimizing some quadratic function over an assignment of weights or over a quantization of weights.
There were a few questions. Yes. So Vishnu basically asks, like, why do Hessians appear here? Like, what do you mean by the Hessian of the model? Yeah.
Oh, so it's because when we think about a local approximation, which is what we're doing when we're learning, right? The first order approximation is just the value of the function. Here, the thing that we're trying to minimize is the distance to the original model. We're constructing a local approximation of that function nearby the original model. So if we think about the orders of approximation, The 0th order part of that is just 0 because the distance of the model to itself, at itself, is 0. The first order approximation to this model, or to this difference, this distance, is also 0 because this is a local minimum. In the sense that if you think about all possible models and then look across all possible models at the distance to a particular model, and you look at that distance at that particular model, at that particular assignment of the weights, because that distance is minimized at that point, and since at a local minimum, the derivative, the gradient must be 0, the first order part of that expansion is also 0. So then to continue our local expansion, we have to go out to the second order expansion. And the second order expansion is a Hessian. And so when we talk about Hessians here, that's really what we're talking about, is a second order approximation of the loss function at some point, in particular at the point where the original model had its weights. And when I talk about the Hessian of the model overall, what I really mean is this whole Hessian, the actual thing that we're trying to minimize, looking at its second order expansion. But practically, we can't do that because that second order expansion is so large, because the size of the Hessian matrix grows quadratically in the number of parameters, in the number of things that you're differentiating with respect to. So we use these smaller sketches that look at the model piece by piece.
Yes. Another question was, can you explain how you make the jump to the last line? I'm assuming it's where you get to the trace.
To this. Oh, yeah. Well, it's just some math. So the expected value of this is just W minus W hat times X. And then W minus W hat times X transpose. So the norm square root of something is just that thing transposed times itself. So we have like this math. Then if I apply this transposed to this component, what I'm going to get is that the X becomes transposed and the W minus W hat becomes transposed. So that's just like arithmetic. And then, of course, this is a scalar, right? A scalar is always equal to the trace of a scalar. And now I can use the rotation formula of the trace. So this is equal to the expected value of the trace of W minus W hat times X transposed times W minus W hat transposed. That's just saying the trace of A times B is equal to the trace of B times A. And now I'm just going to let H be equal to the trace of X transposed. And I get this. So H here is equal to the trace. The expected value of X transpose. And this is part of the reason why this is used practically, is that the Hessian that we use for the second order approximation is literally just the second moment matrix, the empirical second moment matrix of the activations that are input to the layer. And that, unlike a lot of complicated derivative-based expressions, that is something that's actually tractable to compute.
Yeah, also, I also have a quick, Chris, can you hear me?
Yeah.
I have a question. This is actually early part of the talk, but I thought it would be nice. So one question I myself keep receiving, which is, I think you talk about weight-only quantization here, but you decide not to talk about activation quantization. But it would be nice for you to touch on kind of the scenario where people should use activation quantization versus weight-only. I mean, things like training should use activation, inference should do weight-only quantization. But also, at different batch sizes, there are different regimes where different quantization actually more beneficial. So, but necessarily, if you can touch like a couple of comments on what scenario we should use weight-only versus we should use weight plus activation.
Absolutely. So here for weight-only quantization, right? The weight-only quantization is really important in cases where you are memory bandwidth bound, which has been the case for a lot of generative AI. And the reason for it is that, especially when you're not using speculative decoding, every time you generate a token from a large language model, if all you're doing is just generating that one token or not doing anything else, the memory that you have to load from from RAM onto your accelerator is equal to the size of the model, because you need to use every weight. Again, assuming you're not doing anything like mixture of experts, speculative decoding that gets in the way of this, naively, you're just using the size of the model. And so what's bottlenecking your speed of generation, your latency in these applications, is usually that model size. Weight-only quantization reduces that. Activation quantization actually doesn't really impact that much. What activation quantization really lets you do is two things. And honestly, they're very different from each other. And we can often think of this as like two different ways of quantizing. One of the things that activation quantization lets you do is use better, faster floating point accelerators. So if I quantize my weights to 2 bits, but then when I'm doing computation, I take those weights and I decode them to 16 bits, and then I do a 16-bit multiply using the 16-bit tensor cores, my application is proceeding at a rate that is limited by the rate of the 16-bit tensor cores. If I take my activations and quantize them to 4 bits, and I take my weights and quantize them to 4 bits, and I use the FP4 tensor cores, I'm basically able to go like 4 times faster in terms of flops. The trade-off being that when I have activation quantization, I can't do much of the stuff that I'm going to talk about here. I'm basically forced to do the naive rounding because this question 3 of not too much time to compute and compress, it just becomes way more important for activation compression. For activation compression, you can't afford to spend any time at all on quantizing. You gotta do it immediately. It's on the critical path of your inference. For weight quantization, you can actually afford to spend several hours, even days, before you run inference on doing the weight quantization, on producing better weights.
Yeah, this is an amazing answer. Thanks.
Yeah. And then the other half of the answer, the other thing that it does, is activation quantization can help you scale to longer context by compressing your KV cache. So the KV cache in large language models is really an activation. Like those are activations that are simply stored from the previous layer. If your activations are stored in smaller numbers of bits, then you can scale out to longer context because your KV cache doesn't fill up memory as quickly. And this is in some ways a separate consideration, the compute consideration. And because of this, it may be reasonable to spend a little bit more time in compressing the KV cache than you would use in compressing regular activations. If you're thinking about compressing activations where you're going to compress every activation in the model, that's got to be really fast because that's a significant fraction of your compute. In fact, you have to do it to every signal that you compute. If you're just doing it to the KV cache is a relatively small fraction of the activations that you're computing. You may be able to do something more complicated. And this is why typically if you look at papers that are doing quantization, you sort of see this separation of methods. There's weight quantization methods, there's activation quantization methods, and there's KV cache quantization methods for quantization for inference. And then separately from that, there's this whole other tree of methods, which is quantization for training.
Yeah, this is actually very nice. I think that the fact KV cat compression is like different categories is actually a perspective that I think is very, very nice to hear.
Yeah. Well, there's a lot of really cool work in that space. Are there any other questions outstanding?
There was a question. I think this was with respect to something you said, so I'm not entirely sure. But they said, so quantizing again loads the whole quantized model on RAM and then to the accelerator.
Yeah, that's correct.
Okay.
So like typically, at least for the quantization methods that I'm talking about here, these post-training quantization methods, the way that you would do it if you were running that on GPU is that you take let's say it's a 2-bit per weight model. You take your model, you're storing it in high bandwidth memory on the GPU memory in the 2-bit representation. When you go to do computations with the model, you're loading those weights in that 2-bit representation onto the GPU. And then on the GPU, as it's doing the matrix multiply, it decompresses those weights to whatever format you're using to compute. So FP8, FP16, BF16. It does the compute, and then it continues the computation. And then the key thing is that the big FP16 or BF16, the decompressed weights never actually hit high bandwidth memory. So it's not like using a zip file where you would take the compressed file, decompress it, and then have the decompressed file on disk. The decompressed data never actually needs to go over to that thing between that gap between the GPU memory and the GPU itself.
It's a great answer. Yeah. All right, that's it for questions, though. I think for now. So.
All right. So now, where did my marker go? There it is. So okay, I've reduced this to this math problem, and the math problem is something like, find, or let's say we want to find or minimize over W this trace of W minus W hat, or W hat minus W, times H times W hat minus W. And this is over W in some quantization scheme. And for simplicity at this point, just to introduce like the math and the idea, I'm going to say W hat is just in the integers. Obviously, this is like a hand wave, because practically when we quantize, we're first going to scale everything so that it like fits in a realm. But it's easier to express the mathematics when you write W hat in the integers. And the key sort of insight that we have about this model is that this is, in some sense, I didn't write the transpose. Okay. And actually, I'll even think about this in an even more simplified setting. Rather than think about compressing a weight matrix, let me just think about compressing a weight vector that looks like this. So we don't even have to deal with a trace. We just have some quadratic form that looks like this. So that's our problem that we're trying to solve. This is actually, if you think about it hard enough, this is identical to a closest vector problem over lattices. There are actually a couple of ways to solve this. So the analysis that we did looks like the following. So it basically says, suppose that we can decompose the matrix H as H is equal to LDL transpose, where L is a lower triangular unit lower triangular matrix, and D is diagonal and non-negative. This is called a LDL decomposition. It's related to the Cholesky decomposition. And you can basically always do this for any positive definite matrix H. And your matrix H is guaranteed to be positive definite because it's, well, practically because we regularize it to be positive definite. So if we use this linear algebraic transformation, our objective becomes, and I'll call the objective L, the objective becomes W hat minus W transpose times L DL transpose times W hat minus W. And now what I'm going to do is I'm going to choose a way of quantizing so that the quantization error is small. And the trick is to observe that what I would like for this quantization error to be small is for the error of the quantizer to be equal to this. And when I say the error of the quantizer, what I really mean is the thing that I round minus the original thing should be equal to this. And so then that's something that I can do. So I can say, I'm going to sort of imagine that there's a thing that I'm quantizing. Let's call that Z. And then the thing that I quantize minus that thing, right, should be equal to L transpose times W hat minus W. Now, after we quantize, right, the thing that we quantize, this must be W hat. Obviously, right? Because W hat needs to be the quantized thing. And so if we solve this for Z, the thing that we quantize, we get W hat minus L times W hat minus W is equal to Z. And this basically immediately suggests the following quantization algorithm, which is to set W hat equal to quantize the quantization function. Actually, I'll write explicitly round because that makes it more explicit of this. So where round just means round to the nearest integer. Now, here's the trick. Like this whole thing that I just derived, this seems like it's like totally invalid and ridiculous. And the reason why it's invalid and ridiculous is that I've just set W hat equal to itself, right? Like you can't produce a rounded number. You can't produce a quantized model given an expression that already has the quantized model in it. But this is the reason why I did this decomposition. Because another way that we can write this is as W hat equals round of I minus L times W hat minus W. Sorry, minus W, that's not right. Plus L W. And the thing to realize about this expression is that I minus L, because L was a unit lower triangular matrix. So it's a lower triangular matrix with the identity with all ones and its diagonal. I minus L must be a strictly lower triangular matrix. So it's a lower triangular matrix with only zeros on its diagonal. And so what this means is that if we look at the first entry of W hat, and we expand this out, the first entry of W hat is not going to depend on W hat at all, because all of the entries in that first row of I minus L are 0. So we can compute the first entry of W hat based solely on L times W. And then we can do the next entry of W hat. And the next entry of W hat will only depend on the first one, because this is a lower triangular matrix. And so even though this seems like it's intractable, like you're rounding the model based on itself, what's actually happening, because of the lower triangular structure of this decomposition, is that you're rounding the first weight and then using the error of rounding the first weight to round the second weight, and then using that error as feedback to round the third weight. And then you basically just continue this for the whole model. So at every step when you're rounding the weights, you round them in order, and you round them in such a way that the error feeds back and sort of corrects itself. And so, what's the point of this? Why do we do this? Well, the trick is that now, because we replaced this thing with the rounding error of the quantization algorithm, and because the quantization algorithm that we did here is rounding to the integers, this thing must become a vector whose entries are each individually no larger than 1/2 in magnitude. Because if you have the rounding error, the quantization error of rounding to the integers, you get at most 1/2. And so what you can show is that this error is bounded by 1/4 times the trace of D. The reasoning behind this being that this is a diagonal matrix scaling essentially a dot product of two vectors, where each entry in these vectors is at most 1/2 and at least minus 1/2, because they're rounded. Okay, so that's all very well and good, right? What we've shown is that by doing this correction, we're able to get something that looks at and uses H to decide how to round, which is good. And we're able to get this bound, and you can show, although I won't show it here, that this bound is tighter than what you would get with naive rounding. This whole algorithm, it turns out, even though I derived it in this kind of way involving matrix decompositions, it's equivalent to a bunch of stuff that's been done before. So it's actually equivalent to the algorithm used in GPT-Q. And some recent work out of Dan Alistair's group has shown that this is equivalent to the classic Babai algorithm for solving the lattice closest vector problem. So a lot of interesting maths there. But the part that's sort of novel and interesting about our work here is showing that you get this bound. And the bound is interesting because it tells us something about when we might expect this algorithm to do well. In particular, if you look at doing the same thing, like the same analysis with just naive rounding. So we don't do any of this correction. We just set W hat is equal to round of W. Then the natural bound that you would get from this would be that the loss, this proxy loss, is less than 1/4 times the trace of H itself. And again, I won't actually derive that, but you can sort of look it up. And what's really cool about this is that this sort of suggests that the time in which we would expect to be able to get an improvement from doing this sort of clever adaptive rounding using the Hessian instead of doing naive rounding is in cases where this trace of D is small relative to the trace of H. Now, when is the trace of D small relative to the trace of H? Well, it turns out that it's possible that it's not small relative to the trace of H. You can easily find matrices for which the trace of D in this LBL decomposition is equal to the trace of H. A really simple example is the identity matrix. So for the identity matrix, this decomposition is basically just I is equal to I times I times I transposed. And so D is equal to I. The trace is the same. And in general, if H is diagonal, you get the same thing. So if H is some diagonal matrix, you get D is equal to I DI. And this is actually a bit instructive. This math suggests that somehow the worst case scenario for doing this type of adaptive weight-only quantization is when the Hessian that you're trying to use to round is diagonal or close to diagonal. And so you might think, okay, it's unfortunate, but we can't control the Hessian. So maybe this will tell us whether rounding works well, but it won't tell us, it won't really tell us anything useful. But the trick, or the consequence of this, is that it turns out we can, to some extent, control the Hessian. And in particular, one way that we can control the Hessian is by introducing rotations into the model. So in particular, if right before my weight matrix of my model, I multiply the activations by a random orthogonal matrix, and then I sort of fuse that random orthogonal matrix into the weight matrix, and I do the same thing on the other side of the weight matrix, then what I've essentially done is I've rotated the basis that the model is acting in. I haven't actually changed what the model computes, really. I'm just rotating the basis. And a nice fact about random matrices is that on average, if you do a random rotation of one of these Hessian matrices, then you can kind of show that the trace of D is small relative to the trace of H, and it sort of scales approximately as the trace of H to the 1/2 squared divided by n, which is small relative to the trace of H. Now, all of this is to say that if you do a bunch of math, it sort of motivates the idea of trying to produce Hessian matrices in your model. And remember, these Hessian matrices represent the activations of weights going into a layer that are, kind of far away from being diagonal. Another way to call this, or another term that we use to describe this in machine learning, is incoherence with the basis. And so this motivated the method incoherence processing. And the paper that we proposed this in from a couple of years ago proposes the method QUIP, quantization with incoherence processing. And all that we're doing with the incoherence processing is essentially we're multiplying by a random matrix. In the original paper, we were doing something complicated with Kronecker products of matrices, but it turns out it suffices to multiply by a randomized Hadamard transform, which is very fast to multiply by. In fact, you can multiply in log linear time. And that just turns all of these Hessian matrices into something that is incoherent with the coordinate basis. And right? And then basically all this theory goes through. However, right, you guys probably aren't super interested in the theory going through. You're interested in results. So here's the high bit. Back when we originally proposed this, we were able to get down to 2-bit LLMs, say Llama 3, sorry, I think it was Llama 2, 70B, with very little degradation in performance. And even if you, one other nice thing about this random multiplication is that it helps with outliers. So when you do a random multiplication, suddenly all your examples are, or all of your signals are approximately Gaussian. They kind of look like white noise, which is really nice. Makes it very easy to figure out the range. You don't get outliers so much. We have a bunch of follow-up works. So our second paper in this space was called Quip Sharp. The main thing that this adds is vector quantization. Vector quantization basically says rather than quantizing each individual parameter, each scalar separately, we're going to quantize many of them jointly. So in the Quip Sharp paper, we used a vector in R8, and so we quantized each group of 8 weights together. That actually produced a big improvement over Quip. You can show this theoretically by using analysis from signal processing and from information theory, encoding theory. Our next work improves this further. So this is called Q-tip. This is quantization with trellis coding and incoherence processing. And trellis coding is actually a method that was developed for coding theory in like the 80s and 90s. It's almost like using a random number generator. In fact, this is a good, reasonable way to think about it. You have some random number generator that's designed to produce a sequence of pseudo-random Gaussians. And the random number generator is seeded with a source of information that uses a certain number of bits per generation. And then essentially what a trellis code does is it says, well, I'm going to use that random number generator, that pseudo-random number generator, as a decoder or a decompressor, which basically produces a Gaussian distributed thing from a sequence of random bits, except rather than having a sequence of random bits, I'm going to choose those bits carefully so that the pseudo-random number generator happens to output something that's close to the model that I want, or to the weights that I want to encode. This sounds like a crazy idea, but it actually turns out that it's really tractable to find these bits using dynamic programming. And so it's actually very widely used, or was very widely used in telephony back in the day. And the thing that enables us to use it here for quantizing neural networks is exactly the incoherence processing that, by virtue of multiplying the weights by a random matrix, makes those weights look approximately Gaussian, so that we can apply techniques designed to compress things that are approximately Gaussian. And the last paper that I'm just going to briefly discuss is called Yaka, yet another quantization algorithm. And the main thing that this does is it says, well, let's look at a better Hessian sketch. So remember, way back at the start of the talk, I said, well, using the real Hessian of the model, the thing that we actually care about, is intractable. So everybody uses this Hessian sketch for rounding. And I think this is the first paper in this line of work that says, well, we don't have to use that adaptive rounding sketch. We can actually find other sketches, other ways of approximating the Hessian that do a better job of approximating the Hessian, still make this type of adaptive rounding with this linear feedback tractable and get better error and come closer to the original model. The last thing that I want to touch on very briefly is there's this paper, and I'll erase this. Training LLMs with MX FP4. This is just going back to the, going outside of, the post-training quantization scheme and talking about training LLMs with low precision things. This is a paper that, it's not my paper, but it's a couple of my students are authors. And they also use this incoherence processing, also use the randomized Hadamard transform to improve the conditioning of models during training, if I'm remembering correctly. And so it sort of shows that the power of this method of changing the basis at random actually exists or works beyond just beyond just post-training quantization, beyond just inference. So it's kind of a tool that has a good place, I think, in our toolbox when we're rounding. And I want to give enough time for you guys to ask questions in the remaining 30 minutes of the slot. So I should probably stop there.
Yeah. Actually, so thanks, Chris, for the extremely nice presentation. Actually, I think there's a lot of comments in the chat. We see people really love the presentation format. Actually, I have 3 questions actually, but maybe I'll ask all 3 questions. You can answer in order.
Great.
I think my first question is for the specific choice of the Hessian. So you choose Hessian to be sort of the LDL decomposition, and you show that the LDL decomposition has this nice linear feedback kind of things, which is nice. But also the question is, what's the reason? Sort of what's the geometric interpretation of the LDL? I mean, we know if we can do like diagonal approximation, we can do quantum approximation. What's the sort of intuition behind the LDL decomposition? Other than that, it's very nice to derive an actual practical algorithm.
So the way that we actually got to it in our paper is we said, let's consider the family of algorithms that round with linear feedback. So concretely, at every step when you quantize, you're quantizing based on a linear function of the weight that you're quantizing and the quantization error of the previous weights. And then what we did is we looked at the expected error of that rounding method, supposing that we did stochastic rounding on a vector that's in random position. And by random position, I mean that like each individual weight is like uniformly distributed between an integer and the next integer. Like there's no weird rate here. And you can actually then write this out. It becomes a convex optimization problem. It actually becomes I think a positive, it becomes a second, I actually don't remember whether it's a second order cone program or a semi-definite program, but it's a convex optimization problem. And you can actually solve the convex optimization problem analytically, which is unusual for convex optimization problems. And the solution of the convex optimization problem is exactly the LDL decomposition.
Oh, that's interesting.
So the motivation of this, like in describing this algorithm on the board, I kind of just dropped that out of nowhere. But what it is it is actually the optimal algorithm among all algorithms that round using linear feedback. At least it's optimal in the regime where you are assuming that there's no overflow. It turns out that if you assume that there is overflow, that changes the convex optimization algorithm a little bit. And there's actually a slightly different, theoretically optimal L that you can pick. But in practice, we just use this one because those theoretical considerations don't seem to be that important.
I see. That's very nice. So my second question is sort of touching sort of the quip, Q-tip, and then the Yaka side of things, which is there's a little the Hadamard rotation is extremely nice. When I first learned about this, I thought this is very clever ideas. But it seems like from the I don't know how. So a lot of practical models, it seems like the user rotation is very limited. Is it because the computation cost, okay, is n log n, but still it's n log n price to pay? Do you think that's the reason, or do you think why rotations being, despite being extremely nice, hasn't seen that much adoption in practice?
So I think that it has weirdly almost seen more use in training than inference. I think the problem for randomized rotation is that it's not even the n log n, but it's the latency of calling the kernel.
Oh, because that's, even though it's cheap, like algorithmically, sort of n log n, the fact you call a kernel, this is like that is the part people don't want to pay.
And the thing is, like, the naive way of doing a randomized Hadamard transform, it's basically the same thing as a Fourier transform. It's a butterfly algorithm.
Yeah.
And so naively, the way that you get this log n is that you're basically calling log n kernels. And each one of them does n work. And that's problematic when you're bound significantly by the coordination time of these kernels. So what you have to do is you have to have a fast thing that implements this, and it's taken a while for people to implement it. I think that just recently this has been implemented in VLLM.
That's interesting. I do remember there is, I think Tree has a kernel for doing fast Hadamard product, I believe. But it seems like I'm not aware of people having Fuse kernel for doing both. But by my knowledge, this has been a little bit outdated.
Yeah. So just to give an example, it's just yesterday.
Oh wow.
VLLM released it. So like here's a tweet. I don't know if I can well, I don't know if I can post it in the chat here. But this
maybe
is,
you can post it in private. Well, Alex, can you forward this in the comments? Because I don't.
It's like the most recent tweet from the VLLM organization, and it introduces QUIP transform support. And SpinQuant, by the way, is another algorithm that does something similar, and it has this really nice improvement upon QUIP that it eliminates a whole bunch of the randomized Hadamard transform. So our original work did a randomized transform before and after every linear layer, and SpinQuant cleverly fuses a bunch of these so it doesn't have to do them. But these things are complicated, and so the fact that it's been implemented in VLLM indicates that there are people who are using them. The fact that it took so long, I mean, QUIP is a paper from like a couple of years ago, it indicates the complexity of it from an inference perspective.
Yeah, which is also a really interesting research idea for like people interested in the kernel side of things, how to implement a very nice kernel for those kind of things.
Yeah.
So
it's definitely doable, but part of the other thing is that you get more benefit out of it when you're able to compress more. And more modern machine learning models are a little bit less compressible than the older ones. So like we were able to get Llama 2 down to 2 bits. Llama 3, a little bit harder to get down to a lower number of bits.
Yeah. I do think there's a lot of questions in the chat, but I do want to ask one last question, which is the last point you touched on, which is that's precisely my question, which is most of recent models. I mean, just a lot of research show that the more better the model, the more like chinchilla, I guess, like 100x chinchilla law of the model, the harder it is to quantize the model. So do you think that this becomes there's a limitation to quantization, at least only quantization, or do you think there is a lot of room for improvements?
I think that there's still some room for improvements, but we're running out of algorithmic improvements, or rather, we're running out of. What's the right way to say it?
We're running out of bits we can use.
Yeah, I think that if you think about these 3 papers as a sequence, like QUIP, Sharp, QTIP, in some sense, the improvements that we're making there are about improving the compression theory or the coding theoretic baseline for the compressor. And that potential improvement, I think, is mined out because QTIP achieves or allows you to achieve the information theoretic optimal for coding a Gaussian. So if we want to do better than this, we have to somehow leverage structure in the weights, as opposed to using the Hadamard transform, which destroys that structure.
Yeah. That's actually a very good perspective.
Yeah, and so we often want to not use Hadamard transforms, like if we're using NVFP4 or MXFP4. Sometimes we want that big dynamic range because that's where these models work well, and then you don't want to do a randomized Hadamard transform.
Interesting, because that's kind of we start making some structural assumption in the model, which is probably true in many cases.
Right. Randomized Hadamard transform is in some sense the right thing to do when you're quantizing to something that looks like the integers. Yeah. And if you're quantizing to something that doesn't look like the integers, maybe you want to do something else.
Yeah, that's a good point. Yeah, I'll let other people ask questions. Yes. But thanks for all the answers.
Yeah, thank you so much. I think I'll just go through the chat questions and save anything I have for later. So let me start here. I don't know if this is a question or more so a comment, but we could turn it into a question. Basically, Aiton is asking, like another decomposition you might consider, like in your minimization, is taking the L or the Cholesky square root and applying QR decomposition, and then using the upper triangular matrix that falls out. And they're saying this is equivalent to greedy rounding in a lattice.
Yeah. Okay. If you take the Cholesky square root, I think that's QR. I don't know what that would do. Oh, wait. So if it's a QR decomposition on the Cholesky square root, no, that's okay. If I take the Cholesky square root, right, that's just a triangular matrix. And if I apply the QR decomposition to a triangular matrix, the R is just the same triangular matrix. So this is just equivalent to I think, taking the Cholesky decomposition, which I think is the same as this LDL. It's just that you have to factor out the diagonal part so that you can do this correction. Like, otherwise, if you just use the Cholesky square root in place of L, you run into the problem that it's no longer something that you can run in order. It depends on itself, and then who knows?
I see. Let's see. There was a lot of discussion, so I just need to filter through what is actually a question and what is not.
Hopefully, it's positive discussion. I can't see any of the discussion.
If you go on YouTube, you could probably see what the comments are, but I can read some of them out. What is your thought on different precision that don't use mantissa given higher dynamic range but loss of precision?
So different precisions that don't use mantissa.
Yes, I think.
Well, so I'm not aware of any precision formats that people are using that don't use any mantissa at all. That would be pretty low bits, but certainly NVFP4 and MXFP4 only have one mantissa bit, or two, depending on whether you count the virtual mantissa bit. And these actually work pretty well, as it turns out. And part of the reason for it is that you get the higher dynamic range, and these methods use block scaling. So it's not just the floating point number by itself, the 4-bit floating point number, that wouldn't work. But a block of 16 or 64 of them are scaled together with a single scale factor. And that actually gives you enough precision to do useful things, both at training time and at inference time. So it just works pretty well. And the really nice thing about these formats is that they have tensor core support. So you're getting the accelerated compute.
Another question is, does EXL3 not have an implementation of the Hadamard operations in QTIP?
I think it does. But I could be misremembering. I haven't actually used the EXL3 myself. I'm just remembering what people have told me.
There was a follow-up to the previous one. They were saying UE8M0, I guess, is a format.
Oh yeah, but I thought that UE8M0 is just used for scale factors in MXFP4. and in other MX factors. Like it could be that somebody is using it just to encode the weights by itself, but if so, I haven't seen anybody do anything successful with it. But I mean, there's so much literature, it's possible that I've missed something.
Another question is, do you think that we've saturated post-training quantization and quantization-aware training works better right now?
I think that for large language models specifically, we've sort of commoditized, I wouldn't say saturated, but commoditized post-training quantization. We have a pretty good sense now, given a new model, of how to do good post-training quantization. Generally speaking, quantization-aware training is going to give you a better model than post-training quantization. It's just that you have to work more for it. The trade-off is different. So I think that we're increasingly going to see quantization-aware training used more for the most popular, largest scale models in domains like text. And we'll still see post-training quantization used in other cases where people don't want to spend a huge amount of time doing quantization-aware training, or in other domains where a quantization-aware training recipe isn't as well established.
Sorry, I'm speeding through these so everyone can get their questions answered. Maverick asks, or he says, I checked the weights of small LM2. Almost everyone is between is just plus or minus 1. And so why are weird formats like E1M7 not more common during training? And even in quantization, why do we need E4 for just plus or minus 1?
Well, I expect the answer is that the almost is doing a lot of work there. In a lot of cases, even if almost every weight lies in a region, the weights that are outliers are often very important. So, and I haven't looked specifically at small LM2, so it's possible that it's different than the models that I've looked at. But I think that the reason why for typical models you wouldn't see this is that overflowing is bad and that these outliers are actually doing something. Now, it's also the case, by the way, that the question is loaded with the assertion that E1M7 is a weird format. Okay, actually, E1M7 would be a weird format because it has no sign bit. But if it was S1M7, that's just int8. People have trained using int8. And that's something that you actually can do. It's totally possible. It's just that people have found that you really want, ideally, more dynamic range than that.
Let's see.
I think there's a question from Andre. I don't know if you can see this.
Yeah.
I think Andre asked, have you noticed if reasoning models are noticeably harder to quantize due to fragility of reasoning process and the PTQ leading to repetitions?
Sorry, I didn't hear the last thing you said.
Yeah, so
have you noticed if reasoning models are noticeably harder to quantize due to fragility of the reasoning process and PTQ leading to repetitions? I mean, I've seen some cases where they're harder to quantize, but in most cases, I don't think that there's like a huge gap. Like it is definitely the case that if you want your model to actually produce exactly the same sequence of reasoning, then you really need it to be very close to the original model to do that. But if you're just looking at like the accuracy on some benchmark or on some test, quantized models do work pretty well. Like a lot of the modern reasoning models, like even GPT-OSS, right? That was released in FP4. That's pretty highly quantized. And that's a reasoning model. Works pretty well.
I'll do 2 more questions in the interest of time. Aiton asks, there's an interesting phenomenon where fine-tuned models, say for alignment after quantization, are no longer aligned. Do we have a solution for that?
Well, I think that there's a practical solution to it, which is to release an already aligned quantized model. So like GPT-OSS was released in FP4. People are just using it in FP4. And because of that, they're using a version that was aligned. So if you release first-party quantizations that work pretty well, usually using, I assume, quantization-aware training, then people are more likely to just use the thing that you released, and then it would be aligned. It is definitely the case that quantization as an attack on alignment to try to de-align a model is definitely something that can happen. But I don't think that it's it's not as if it's the best available attack. Like if I have the weights of a model and I want to remove the alignment, there are other things that I can do that will be more effective at removing the alignment than just quantizing it. So the thing I think we want to avoid primarily with quantization is the workflow where somebody quantizes the model in good faith, not trying to unalign it. And then the model becomes unaligned as a result of the quantization. And releasing already tested quantized models seems like the most straightforward way to avoid that problem.
Okay. The last question is, what are your thoughts on leveraging sparsity for extra compression? While flash attention supports blockwise sparse, I'm not sure if the microscaling formats support block sparse representation.
Yeah, people have tried this. It kind of works. I think that there's been a lot of work on trying to leverage NVIDIA's 2 out of 4 sparsity for things. A lot of this stuff works. It works pretty well. It's just a question of what the trade-off would be compared with just reducing the number of bits. And I think that practically, I haven't seen any works that show convincingly a sparsity, like an unstructured sparsity-based method that competes favorably with just reducing the number of bits as a post-training compression method. For sparsity during training, you can definitely get away with a lot, but it is definitely also true that if you look at the models that big AI labs are releasing, even the models that are quantized, like GPT-OSS, I don't think that they're using unstructured sparsity. And the type of sort of work that you would want to do with sparsity is in some sense being done by mixture of experts layers, where you're essentially, and granted, mixture of experts layers are not like sparsity exactly. They don't actually increase sparsity doesn't increase the dimension in the way that mixture of experts layers do, but they both have the effect of allowing the model to seem like it's operating on a larger space while having a smaller number of flops. And so a lot of the benefits that you might traditionally have looked to get from sparsity, maybe MoE is going to get that these days.
I see.
But it's a very hand-wavy answer.
I think that is it for today. Thank you guys so much for coming. Thank you so much to Chris. And tomorrow we will have Songlin talking about positional encoding work. But again, yeah, thank you guys all for coming, and we hope you have a great rest of your day.
Yeah. Great.
Thanks, Chris, for the very nice